live? The last year's version? Is there a new one?
There's a new one. I'll explain and share the thing. Because I don't think the new one's on the website yet. Desktop.
You don't need it actually, because if you're webcam on the, I think you'll be sitting behind this thing anyway, right?
Yeah.
So you can
Yeah.
use your laptop.
Oh right. Yeah. Yeah. Actually, I want. Yeah.
What's the plan?
So what I'd like to do is have my. I can just mirror my scene. Should be fine. Yeah. I think I'm good to go. Let's see. I'll share my screen. Okay, I think we're just about ready to go. So, hello everyone. Thanks for coming. I think I am. Yes. Yeah. Hello. My name is David. I'm a PhD student here at the UVA, second year. I'm with Stratis. During my master thesis, I worked with Eric on group convolutions, regular group convolutions, making them more efficient. And today I'll be walking you through this tutorial on regular group convolutions. So first off, I think the tutorial that's listed on the website right now is still the one from last year, and I made some updates to it this year. So I have a QR code for you guys to scan. This will link you to a collab of the new updated tutorial, but we'll also get this one on the website.
Why don't you share that somehow?
Yeah, we're working on that. I mean, what do you mean?
Do you have another way of getting there? Because it's kind of weird to scan a phone and try to.
I can.
Yeah, great idea.
Sure.
Hold it up.
This works. This is an interactive session. This is great, guys. Okay. So this will link you to a collab of the updated tutorial. The changes I made with regards to the one last year are just last year's tutorial was a bit complicated in terms of the actual programming part. So I got a lot of questions about, I used einsum operations, for example, which are very complicated, or people usually find them very complicated. I just rewrote the tutorial to be, I guess, more straightforward, to be more about the essence of group convolutions. So hopefully less questions about the programming aspect of things this year. I think how we can organize this session is I'll walk you through parts of the notebook. So if correct, you should have a version that has parts of the notebook left unfilled. So there's some programming for you guys to do yourself. I'll walk through the one with the actual full implementation in it, just to for you to get an idea of the type of stuff you're gonna be implementing yourself. First off, a question: how many of you picked a project already that corresponds to this module, group equivariant module? There's quite a few actually. Okay. Because I think the idea is that these sessions are also supposed to be when you meet your supervisor, like your project supervisor. So today we only have Miltos here. I think you're supervising the long-range graph benchmark project. I think I'm supervising a project on equivariant neural rendering. Nice. But I think since we're all still getting set up, we'll just focus mostly on the tutorial this time. don't think anyone started their project yet, probably. So I think how we can do this, I'll just start going through this notebook, and if at any point anyone has any questions, feel free to ask them. Yeah, maybe starting out, are there any things that you'd like to have revisited from Eric's tutorial that he gave this week? We have the man himself here, so if there's any big questions currently, then we can do those first. I don't think I see any hands, so let's just get started. So this notebook starts out with a brief introduction on what the idea behind this notebook is for you to implement regular group convolutional networks from scratch, only using PyTorch. And yeah, so this is the type of code block you'll see throughout your version of the notebook, with these spaces for you to fill in your own code. And they should also contain comments which sort of direct you towards a correct implementation of these parts. But in this version that I'm showing on the screen, these parts are already filled in. So the notebook itself starts out with a brief recap on group convolutional networks. Actually starts out with a brief recap on CNNs. I guess let's go through that very briefly. You can read all of this yourself. So I think I'll go through this. It's probably going to take about an hour, and then we'll have another hour left over for you to start programming yourselves and ask any questions that you have. So I would say read this the second hour more in depth. So starting out, the conventional convolution operation, which we have here, is the one that you usually implement in convolutional neural networks. So we have this integral over an inner product between a function and a convolutional kernel K, which is a translated version, I guess, of a function over R2 itself. And in conventional CNNs, in reality, we actually implement, since this is a continuous integral, you actually implement a discretized version of this operation, of course. So it just comes down to a sum over the domain of your function, so over, let's say, the different pixel locations, the inner product between your input function, so your image or your feature map, and a convolutional kernel. And then we usually assume that the distances in between pixels are 1 for simplicity, so we end up with this discrete sum. So in GCNNs, you basically are trying to extend this operator, which you have here, from functions defined over, let's say, R2 to functions defined over a group. So we're working with groups that are semi-direct products of this translation group and some group of interest, which could be rotations, for example. So we're interested in defining a convolution operation over the roto translation group, which you see here. So this notation here basically says that all of our group elements consist of a translation part. So this G, all group elements G, consists of some translation in 2D and an additional group element from a group of interest H, which could be, for example, a rotation group or a dilation group. And the first thing that we'll need to do is, since we're operating on 2D images, which are defined over R2 usually, we'll need to lift this function to the group itself. So if we want to implement convolutions on the group, we'll first have to map our input image to the group, right? So this is this lifting convolution that Eric also explained in his tutorial. And essentially we do that by more or less what's happening is you're just applying for a given group element. So this group element consists of a translation, and in our case, we're going to be working with rotation. So a translation and a rotation. You're just applying this roto translation to the kernel function, and then applying the kernel. So normally you'd only translate the kernel. So you only have this translation operation happening to the kernel. And now we're actually working with also a rotation operation. So essentially this is a rotated and translated kernel. And this is also what we're going to be implementing first in a bit. This idea of applying a rotation operation to this kernel function, and for that we'll need to actually apply this transformation to the domain of this kernel function, so to R2 in this case. So we're going to be transforming or rotating a grid defined over R2 by a set of group elements. Okay, and then if we have lifted the input image to a function on the group, so we now have this function fout defined on the group, which maps from the group to a real value, we can actually implement the group convolution operation itself, which is now an integral no longer over R2 only, but over the entire group. Which also means that this kernel function that we're now using is also a function defined over the entire group. So maps from the group, from any group element to real value. And because we're working with this very specific type of group, which is the semi-direct product between translations and rotations, our convolution operation factors into these two integrals essentially. So this is also how you sort of implement it in the end. So you're just applying your rotation operation to a bunch of kernels first, and then you actually use PyTorch's convolution operation to apply them to your input feature map. Okay, so and then finally, after a bunch of these group convolutional layers, we want to obtain a representation that is invariant to the group action. So these group convolutions give you equivariance to roto translations, right? So essentially meaning that if you have a rotation operation you apply to the input of your network, this means that the activations will not change, but they'll transform. They'll basically move to a different part of the feature map, so you can see. So all information is still retained. It's only located in a different location in the feature map. So this gives us a feature map or a network, I guess, that is equivariant to rotations. But ultimately, we're often most interested in having networks that are actually invariant to rotations, right? Because if you want to classify an image, for example, you're assigning a single label to a full image. So you'd like, in the end, to have I guess a feature map or a feature vector that is invariant to any rotations that you apply to your input. And you can just do that by projecting over the remaining spatial and rotational dimensions of your feature map. So essentially just a pooling operation applied to your feature map over the spatial or over the entire group. And you end up with a feature vector which is essentially collapsed into a single point, and you can use this to classify your full image. Okay, any questions on this very brief recap of the basics of GCNNs? Yes?
You use the term feature map and neural net kind of interchangeably at some point. Could you explain why that is? Because I understood the idea of having like the feature map, also have the rotation.
Yeah.
I guess.
Yeah.
But how do you translate that in the net?
Okay, so I'm not sure I understand your question, but so your network consists of a bunch of layers. So you always start out, if you have a group convolutional neural network, you start out with a lifting operation that maps from your input to the group, right? So it maps from a feature map defined over R2 to a feature map that is defined over the entire group. And then you have a bunch of these group convolutional layers which apply all kinds of nonlinear transformations to these feature maps. And you end up still with a feature map defined over a group, right? At the end of your network, basically. Does that make sense? Yeah. Okay. Any other questions? Okay, then we'll move on. We'll actually start coding. So this first cell just imports all the necessary and installs all the necessary packages that we'll use in this notebook. It also downloads an image that we'll use to verify our implementations of interpolation operators. I should have probably run this before. It's going to take a while to install this stuff, but we'll go ahead and move on. CPU is fine, I think. But it's just going to be a bit slower. But it should also work on the CPU, I think. Should be fine. Okay, so brief recap on group theory. So first off, definition of a group is simply a set and an operation. So a set of elements and an operation, binary operation, which combines these elements, which has these four properties. So closure under the group action, meaning that if you combine two elements of the group, you'll end up with another element of the group. Identity, so that you have an identity element, which when applied to another group element will yield that group element. An inverse, which basically maps any element to the identity. And then associativity, so the group operation distributes, as you see here. And then a group can also have an action, so it can transform functions defined on a space, so functions defined on R2, for example. And this happens through what we call the regular representation. I see the symbols missing. This should be like a fancy looking L. I'll just make it an L for now. So this operator essentially works on functions defined over a space, functions defined on R2 in this case, by transforming their domain, the domain of that function. So essentially how you could see this is if you have a function defined over R2, for example, an image, then rotating this image to the left by 90 degrees, you can get the resulting pixel values by taking this pixel this pixel location and mapping it back to the original image, right? So basically applying the inverse transformation. That's essentially what's happening with the regular representation. So we'll start by implementing all of these properties in a class. So I've implemented a sort of a base class here, which is a torch module, which has all of these properties that we just defined. So basically the initialization function just sort of stores information about this group. So it stores the dimensionality of the group and the identity element. This elements function should return a tensor containing all the group elements for this group. And then we just have a bunch of functions which define the product, the inverse, but also the action of the group on R2, which we'll use to transform the kernel grids that we're going to be working with. We'll need a matrix representation. So a matrix representation for a group element is simply a matrix form, I would say, of the group element. So it is a representation is a mapping from the group to a set of matrices which transform as the group itself. So you can combine these matrices. Essentially, you can, for example, combine two rotation matrices to end up with another rotation matrix, right? So there's this sort of correspondence between group elements and matrices. And this function should return for a given rotation angle, for example, a rotation matrix that encodes this rotation. And we're not actually going to use this function, the determinant of group element. This is used to, if your group has an effect on volumes defined on R2, for example, on a space. So rotations don't change volume, right? If you rotate an object, its volume doesn't change. But if you have a scaling operation, then if you apply this operation to a volume defined over R2, the volume is going to increase, right? So you need to account for this when applying group convolutions. We'll keep it simple and just stick with rotation operations. But if you would like to implement equivariance to dilation operations, then you will need this. But you can read this side note for more information on that. And then we'd also like to have some way to normalize our set of group elements to map them between -1 and 1. And this is simply because the interpolation function that we're going to be using expects inputs in this range. So essentially this function just needs to map from, let's say, 0 to 2 pi to -1, 1. Did I run this cell already? I'll do it again. So then for implementing the cyclic group, the group of rotations by 90 degrees, cyclic group of order 4, we can just basically inherit this class and start filling in all the necessary functions. So I left some hints here, which should help you implementing the product, for example, the inverse and the representation, matrix representation itself. Yeah, so that's basically what this class does, is implement the above methods for the cyclic group of order 4. So essentially all the group elements are just a grid starting at 0, ending at 2 pi. And then, so you'll also re-implement these methods yourself. So don't copy these. You have to figure them out yourself. But I'll just run this cell, and then we can run some tests and see how this implementation actually works. So we can define a cyclic group of order 4 with the implementation that we just made, which consists of 4 elements. So this function should give us 4 elements, starting with the identity element. And then this should be a rotation of 90 degrees. This should be a rotation of 180 degrees. This rotation of 270 degrees. And we just have inserted some assertions here to check whether the implementation you're going to make is also correct. And this checks the representation, matrix representation. So, for example, for the identity element, you would like the matrix representation to correspond to the identity matrix, right? Because the identity rotation shouldn't have an action, a rotation action on R2. And then we'll start using the group action to rotate an image. So we'll open the image that we downloaded previously, and so something we'll need is an interpolation function. We're essentially gonna be transforming the pixel grid that this image is defined over. And so to obtain pixel values for the transformed grid, we'll need an interpolation function, right? That makes sense. For this interpolation function, I just used Torch has this grid sample function, which is a bit weird. It's very specifically made for a type of network which needs to use this interpolation function, but because it's very specifically made for that purpose, it's the requirements for it are a bit strange. Like it expects a certain type of input grid. It expects certain dimensions to be aligned in a certain way. You can just ignore this cell and just use these 2 function definitions. The first one for bilinear interpolation, which you'll be using to obtain transformed grids on R2, and then trilinear interpolation, which you'll use to obtain kernel values for transformed grids on the group itself, 3-dimensional group. And then I have an example of how you could use this bilinear interpolation, for example. So we define a grid, a 2D mesh grid, which is basically just a grid of pixel coordinates, where each pixel coordinate corresponds to one of these pixels in our image. So we'll create that. Then we can inspect this grid real quick to see what shape this has. Might be useful. So since our image is a 512 by 512 pixel image. This mesh grid has a dimensionality of 2, which is the x and y dimensions, by 512 by 512. That makes sense, right? And we can then transform this grid using the function definition for the regular representation of the group. We can just use standard runtime for now. That should be fine. Actually, then I'll have to run everything again. I'll just keep it like this. I'll have to speed up a bit because otherwise it's going to complain that I'm not using the GPU enough. So we have just transformed the image grid, which we can actually inspect. So the original image grid started out at -1 in the top left corner. And this transformed grid should have a different value there. Let's see, it actually does. Yeah. So as you can see, this transformation just mapped this -1 coordinate to the 1 -1 coordinate, which should be a rotation clockwise by 90 degrees, I think. It's the top of my head, but we'll see. Counterclockwise by 90 degrees, I should have said. So this is the transformed image, is the image that we obtain when we use this transformed grid to interpolate the original image. And we see we ended up with a clockwise rotation of 270 degrees, counterclockwise rotation of 90 degrees. So we'll use this function, like this transforming of grids and the interpolation function to obtain transformed kernels over the input domain, right? So remember, we said that to lift our input function to the group, we want to transform our spatial kernel by all group elements. So this means that we need to transform this kernel function, which is, you can also see it just as an image of sorts. We'll need to rotate it by all the group elements, essentially. So that's what we're going to use this transformation function for. Okay. Any questions so far? I think this is all quite straightforward, right? Then we'll start out by implementing the lifting convolution. So the idea, very quickly, is that this lifting convolution will disentangle. It will map from the input space, so to the input space to the group, and it will disentangle features in the input with respect to orientation. So let's say that we have an input which contains these 3 features. We have a kernel which in its canonical orientation can recognize, let's say, an upright version of these features. Then the lifting operation is going to result in a feature map which has this additional group dimension, right? Where every slice essentially of this feature map corresponds to input features at an orientation corresponding to that slice. So the original, like the first sort of spatial slice of this feature map would correspond to all features with the orientation of 0 degrees, and the first one 90 degrees, etc., etc. Does that make sense? Okay, and to get there, what we'll need to do is simply transform our kernel function with the group. So this is just an example of what a regular convolution operation looks like from this point of view. So you have a kernel function, which is defined over the input space. You basically transform it using the translation operation by all translation elements in your input. So these are just all the, I guess, relative positions in your input image. You translate the kernel for each of these relative locations. You apply the inner product with the input, and you end up with a new feature map. So, for example, this activation here is what you get when you translate the kernel to this point in the input image, right? So you basically translate your kernel over the entire image, you obtain activations for each of these locations, and you end up with a new feature map. So this is just what happens in normal convolutions. And now we're going to extend this to also essentially have rotations included in the set of operations. So first, we have a kernel function, we rotate it, and we translate it by all possible group elements. So for every translation in our input, also for every rotation in our rotation group, we apply these transformations to our input, or to our kernel, I should say, and we apply this kernel to the input, and then we end up with a feature map which has this additional dimension now, right? Okay, then we'll start implementing this. Yes. So this, again, is just a base class which implements all the necessary operations on your actual kernel function. So from this class, we would like to be able to sample a set of rotated spatial kernels. So again, we just make this grid similar to what we did before. Now we have a grid which doesn't correspond to the image size, but instead corresponds to the kernel size. So this is just the grid over which your kernel is defined. And then we create a function that transforms this grid by all rotation group elements. So that's what this function is supposed to do. It creates from this original kernel grid a set of rotated kernel grids, essentially. So you just loop over all the group elements, actually the inverse of these group elements, if you remember what the regular representation looked like. And then you apply the group action for this element to the grid, and you basically stack all of these grids, and that's what this function is supposed to return. And then this sample function, we're going to implement it later, but this should give us back the actual transformed kernels. So this function simply returns a set of transformed grids for your kernels, and the sample function should actually give you the convolutional kernels that you're going to apply to your input itself. I think, oops, need to run this first. I also made a visualization for the transformation that we applied to this grid. So we'll inspect that now. So we just create an instance of this base class. We say we'd like a cyclic group of order 4 of a kernel size of 7, and then just randomly 3 input channels on a single output channel. So this is just a check to see whether you've correctly implemented the transformation of the grid. And then here you should visualize the actual transformed grids. So these 4 grids, 4 spatial grids, correspond to the 4 rotated kernels, right? And you can follow this blue X to see that it does indeed correspond to 90-degree counterclockwise rotations. So does this make sense to everyone still? All right, then we'll implement the actual sampling of our convolutional kernel. So we simply create a weight, which is a weight as you would see it in normal CNNs as well, which has a number of input channels, number of output channels, and then kernel size. And we initialize this weight. And then the sampling function simply applies the interpolation operation that we saw before with each of the spatial grids to this weight. And here we fold the input and output channels into the same dimension, because you can just treat these as you'd like the sampling only to go over the spatial part, essentially, of the kernel, right? You could just see each of the input and output channels as separate images over the input space. So for every group element in our group, we apply bilinear interpolation to the weight using the transformed grid that we created earlier, and we simply stack these, and we end up with a set of weights which has an additional group dimension compared to before. So first we only had output channels, input channels, kernel size, and now we have an additional group dimension, and we'll actually shuffle the axes of this weight round, and we'll get back to this a bit later on why we do this. But this basically just swaps these two axes, right? So now the output channels are in the first dimension, group elements are in the second. Then I'll run this cell. And we can visualize the kernels that we've just created. So we had here we had defined a kernel with 2 input channels, a single output channel. So for this single output channel, we're now visualizing the 2 input channels. So the 2 rows are corresponding to the 2 input channels, and then the columns are corresponding to the different group elements. And as you can see, these kernels now also implement this rotating action. So this is 90-degree rotation, right? Okay, so now finally we're going to implement the lifting convolution itself. So we have the kernel defined by the interpolation kernel we just implemented. And then the forward pass is simply going to sample these convolutional kernels. And then through some trickery, we can still use the PyTorch conv2d operation. So the reason that we can do this, it also says here in this comment, the reason we can do this is because we can simply treat each of the rotated kernels as just another output channel, because that's essentially what you're applying it as, sort of. So if you reshape the output channels or the group dimension into the same dimension as the output channels, the weight gets a bit of a different shape, but you can still use this conv2d operation to apply it. So this might require some thinking on your part as to why we can do this and why this is useful. Yes?
What do you mean weight gets a different shape?
So you're basically reshaping here. If you sample this convolutional kernel, this is basically our set of convolutional weights, right? So this has a shape of, I think we defined it up here. Yeah. Output channels by number of group elements, by input channels, by kernel size. And now what you're doing in order to still be able to apply the PyTorch conv2d function is you fold these 2 dimensions into the same dimension. So you get a 1 times 4 by 2 by 7 by 7 shaped weight. Yes.
When you do regular convolutions, you might lose, by design, you might lose some pixels on the edges.
Yeah.
Does the same happen now also depending on the number of group elements? So increasing the number of group elements then also further limits how much you can do per group, right?
Let's see if I understand your question. So I think your question is related to normally we use padding or we don't use padding in normal convolutions, right? And now we have a kernel which is defined over the group, and this group is also has a number of elements. You might want to apply padding there or not, right? That's what you mean? Yeah. So in practice, we don't encounter this problem with the rotation group because our first of all, the rotation group is closed. No, that's not the word I'm looking for. Periodic, right? So if you apply a rotation, 360-degree rotation, you end up with the identity element. So you get back to your original, right?
I can also comment on this. I'm not sure if we interpret the question the same, because I was
Okay.
thinking you were referring maybe to the spatial part of the kernel. If you rotate it 90 degrees, everything is fine, right? Because you stay in the pixel grid. But if you rotate by 45 degrees, then these corners, yeah, they leave the grid, and you can interpolate, but it will return the value 0 if you do padding. So that creates some inconsistency that some rotations see everything and other rotations are not able to leverage the corners of your kernel. Yeah. So in this respect, we typically do apply a disk mask on this kernel such that indeed they're truly rotation equivariant.
Yeah.
Like if you rotate a disk, it will stay a disk. If you rotate a square, you rotate 45 degrees and then crop it up again to the square, there you get this weird shape. So quite often, if you want to have pure equivariance, then we apply a disk mask on top of this. Yeah,
And then you lose a little bit of efficiency because you're basically in the corner if you multiply with 0.
it's true.
Alright,
Yeah. If you have a 5x5 kernel, you would ideally have 25 weights, at least on the spatial part. And now you cut out the corner points, and let's say you only do this for the corners, yeah, then you only have 21 weights, for example. So this is true.
Yeah, so I can actually visualize this, I think. If I wrote my code correctly, we'll see. But since we're only going to be working with 90-degree rotations in this implementation, we didn't apply a circular mask. Actually, I'll up the resolution a bit. Sure. Yeah, so I guess this is what Eric was referring to, that because our kernel is given by this discrete set of weights, which is defined for the sort of canonical orientation of your kernel. If you rotate it by 45 degrees, as happens here, you sort of lose the corners, right? So you sort of are rotating. These pixels come from a location that falls outside of the original kernel in the original orientation. So yeah, to obtain a convolution that's still equivariant in these settings, you'd need to apply a circular mask to the kernel in order to prevent this, I guess. Yeah. Okay. Good question. Then we'll move on. So I recommend you look at this, you read this comment, and I think this hint also sort of alludes to what I was just saying about folding the group elements of your kernel into the output channel dimension in order to still be able to use the convtd implementation of PyTorch. I recommend you read this closely. It took me quite a while to understand, but yeah.
Just to be sure, like when you're creating a kernel, so each group element will share the parameters, right? Because you're rotating.
Yeah.
So I was wondering, like, I mean, wouldn't it be because in this you're using a sort of an extra constraint such that each group element is like you're rotating over a group, but instead of this, if you let it run freely, wouldn't it be always be better?
So you share the weights over the entire group because you want equivariance, right?
Yeah.
So you would like the response of this convolution operation to be the same, regardless of any rotations happening to your input.
I mean, but like if you let the network, I mean, if you don't do this, and instead of it, if you just take this, I mean, you keep the dimension same, but so wouldn't the network learn this on its own?
With enough augmentations, sure, yeah. But I guess like what you're referring to is having separate weights for each rotated version of your kernel, right? So if you would do that, then there's basically no distinction in this line here. There's no distinction between output channels and like the group axis, right? So if your kernel varies freely over both the channel dimension and the group dimension, then this just corresponds to a normal convolution with a larger number of channels, right?
Yeah, I think this is a nice example also of group convolutions being a special case of normal convolutions, like a constraint operator. And so group convolutions are just neural networks constrained to be equivariant.
Yeah.
And now if you do what you do, you basically take away the rotational equivariance constraint, which gets you back to only the translational convolutions. And so you see that also here, because now the output channels are formatted in a special way. That means there's weight sharing over this rotation axis. If you wouldn't do that, yeah, then this would be just a plain conv2d specific output.
But yeah, given enough data augmentation, arguably you maybe get at the same result. But in settings where you want this, or you know beforehand that your data is rotationally symmetric, for example, then you could have your network learn this, but why why would you? If you can just implement it to be an equivariant function always, then that, in my point of view, is a good inductive bias for your model. But this is an age-old discussion, I believe, or criticism on equivariant deep learning. If you just scale up your daytime models large enough. Yeah, that's quite nice. Some background music. Okay. And the last step, after applying the convolution operation, we fold the output channels and the group elements back into separate dimensions, just for clarity. Okay, next we're gonna be working on the group convolution. So now we've implemented the lifting convolution, which maps from our input domain to the group, right? So we have a function defined over the group now. And now we're gonna be implementing the group convolution itself, which means that our kernels are now also defined as functions over the group. So this figure is just a visualization of the group action that we're going to be applying to our convolutional kernel. So difference between group convolutions and the lifting convolution that we just implemented is that the kernel function now also maps from the group to real values, right? So we no longer have only spatial dimensions, we also have a group dimension. And we're going to be applying group actions, which consist of this translation and rotation part, to these kernels. And what you'll see happening is this twist shift motion that Eric also talked about in his lectures. Oh, that's great. I hope Chase is going to ask them to stop. I don't like it. It's very distracting to me. So our kernel function transforms as such with this twist shift motion, right? So we see this spatial kernel corresponding to the last group element moving to the first group element. So there's this action happening along the group axis, a shift, but then also a rotation motion because of the rotation, or because of the action that the rotation group has on the spatial domain. So it both shifts and rotates along this group axis. And apart from this, it's essentially the same thing. So this figure, again, illustrates sort of what we're doing when we're applying the group convolution operation. We now have a kernel which is defined over the group. We still simply apply rotation and translation actions to this kernel. And for each of these combination of group elements, we apply it to the input, which is now also defined over the group. We again end up with a function over the group. Any questions about this part? Is this clear? So, yeah.
I understand probably that what you're trying to do here is like compute an integral transform that basically goes from functions defined on the group to functions defined on the group.
Yeah.
So what you would learn, like when we do this, because it kind of seems like we haven't changed the domain in the same way we have in the previous steps.
Yeah. So this is a very this is the same operation that you would apply in normal CNNs, normal convolutional operations. Only your function is now defined over the group. That's the only difference. And how people usually interpret convolution operation in normal CNNs is a sort of a template matching algorithm. So you learn these kernels, which have these three weights. You learn essentially to extract functions from your input space with a certain shape, I guess I would say. So these convolution operations apply sort of transformations to the functions. Does that make sense?
Yeah, I think so.
So it's just you're doing sort of feature extraction with learned features over the group. Yeah. That's, I think, how I would interpret it, yes.
I don't yet see why you need to transition from only lifting to that step. So to me, the lifting, when we build that stack and then share the weights over all those channels,
Yeah.
I thought there would be already enough to learn an invariant rotation and invariant kernel.
Yeah, that's right.
Why would we need that operation?
Yeah, it's exactly right what you're saying. You could just use the lifting operation, but you'd learn an invariant function. So because your lifting operation ends you up with a function defined over the group, you could simply collapse the group access of your feature map and end up with a function only defined over a spatial domain again, just like your input was, right? So basically you're extracting, using the lifting operation, you're extracting features under the different transformations of your group of interest. So you get this additional dimension in your feature map, which corresponds to rotated features, right? And you could just project over this axis back down again to a 2D function. But now this 2D function is invariant to these rotations in the input, right? Does that make sense? So this lifting operation sort of extracts. Yes, yeah, that's true. But the reason you'd like your network to be equivariant is because if you only have operations that are invariant to rotations, you're not able to distinguish between relative orientations of features, essentially. I think
Now you want to learn in which, not just extract that there's this feature, but also
how it relates. So how it relates to different features also. So I think a common example that people use to illustrate this problem is the Picasso problem, I think. Basically, if you have a face, let's say you have a rotationally invariant operator, which you like to use to extract faces. If you have a face which has the eyes, let's say, oriented like it would normally, but the mouth upside down, then this rotation invariant operator is never able to recognize this. Because it only basically, we're gonna have a very nice illustration of it. It only is able to extract that there are these features in the input, but it can't extract the orientation of these features relative to each other.
So if you have like a neural network that detects eyes at certain locations and a different rotation, so you imagine like the group convolution at actually an orientation axis, right? It says at this location I have an eye somewhere at this orientation or this orientation. And if you were to project it over this orientation axis, you no longer knew which orientation it had. So it could be this one or it could be this one. After this max pooling over orientations, these images look basically the same because you don't have this orientation information anymore. Now with convolutions, you maintain these orientations, and then you know if I want to have a particular face detection, like a happy face, then I want the eyes pointing in that direction and the mouth curving upwards. So that's information in terms of relative position. The mouth is below the nose, and it has a certain orientation to it. And that allows you to make a distinction between this one. Here also the mouth is below the nose, but it has a different orientation. So in order to keep being able to reason about relative orientations, relative positions, yeah, you do not want to collapse this orientation axis.
So this becomes useful once you have larger features that are built of smaller features.
Right? Yeah, exactly. Yeah.
And it's also a bit like with conv nets, you could in principle do one convolution layer and then do a max pooling over to the position axis, but then you're no longer able to detect any patterns that have anything to do with spatial configurations of patterns. You have like one invariant translation, invariant descriptor. So yeah, that's why you want to postpone pooling over these axes as long as possible, because up until that point you are able to leverage these relative positions, relative orientation. Yeah.
So if we have a bunch of these layers after each other, let's say like 4, do we just keep adding dimension? Or
no, and I think that's maybe what you're going to show next. Like the question is, do we keep adding dimensions if we go in depth?
is it just one adding and then we just keep it until we
You could change actually how many rotations we sample in the next layer. It's a bit like also with translational convolutions, you can decide to do strided convolutions, which is skipping every other position and it decreases the resolution on the spatial axis. You could also do that here, or maybe the other way around, that you do subsampling sprites which stride lower than one. The idea is that in these convolution layers, you basically have a kernel, whether it be 2D or 3D, and then you apply it, you rotate it, apply it, rotate it, apply it, and you do that as often as you want to create a fine resolution on output rotation axis.
Is there any theory on basically how to close these? So we have like a 4-layer network. Is it like a theory? Okay, I use say this stride, and here I use that stride, or here I sample this much and here I sample that much.
That's a good question. I don't think there's any
Engineering.
Yeah.
It's a lot of engineering, but there is some theory to it. Like with a 5x5 convolution kernel, you don't have the spatial resolution to detect patterns that are sensitive to orientations smaller than let's say 45 degrees. There's no point in maybe sampling 16 output rotations because you don't have the resolution anyway to make the difference between this and this orientation. But the further you go into your network, these resolutions sort of stack up, and you would, in principle, be able to, in the end, detect finer patterns in the input when it comes to orientation sensitivity, the deeper you get. But this is not what people do or are concerned about. The tip is just fixed throughout, and that seems to work well. Yeah, so it's, I guess also heuristics could be that there are applications where it could make a difference.
I think there was another question. Sure.
I
Question
have the
answered.
same question. I was
Okay.
just wondering that you have to downsample at some point, right? Like if you have 4 orientations at each layer, then at the second layer already you have technically 16 orientations, and then another one and you have 4 times as much. So you have to sample, right? Like,
No, yeah, maybe you can move on to the full group convolution.
Yeah, I will. Yeah, I think,
that'll-
yeah, I hope, and otherwise we'll revisit your question then. So I guess your question is sort of related to, so I'll use this image, I think, to explain. Our input feature map now has this orientation dimension, right? So we have 4 sort of spatial feature maps, which each correspond to a specific orientation. And now we're applying again, for every group element, the rotation operation to our kernel. But you should really think of this as sort of your input group dimension, because this feature map just has an additional dimension defined over the group. And then your kernel is also going to have sort of an output group dimension. So your kernel is just a function. This K is just a function defined over the entire group, which can vary freely over the entire group. So essentially, for this location right here, it could have a different value than for this location here or for this location here. And then we still retain equivariance by applying the group action for every rotation and every translation to this kernel defined over the entire group. So yeah, your input feature map and then also your kernel has this group axis. So it corresponds to 4 different group elements, but we're still going to apply also the action for these 4 different group elements to the kernel itself. But you should think of these as 2 separate sort of dimensions, I guess. That would be the most convenient. But let's look at some code and maybe things will become a little bit clearer then. So we're gonna, similarly to what we did in the lifting convolution, define first the grid for our kernel in this base class. And now our grid sort of consists of these 2 separate parts. So we have a grid defined over the spatial domain and a grid defined over the group axis. And we can then combine these 2 to obtain a full grid over the combined spatial and group domain. So this grid, spatial grid, still looks exactly the same as it did before. So it's just kernel size by kernel size, running from -1 to 1. And then the grid over H is just a tensor of all the group elements, right? And then this function, this create transform grid, should transform the grids corresponding to this operation that we saw here. So we just defined a grid over a spatial domain and a grid over the rotational axis. And now this transformation function is going to combine these 2 grids and apply this this action to it, this rotation, twist shift motion that we saw previously. So we sample the group elements again. So this, I guess this corresponds to what I was just mentioning about sort of the input and output group elements that you could think of. So these elements are ones that we're going to apply to our kernel grid, but these elements, this grid over H, is just the grid over which our input function is defined. Does that make sense? So we're still going to loop over all the group elements, and we're going to transform the spatial grid with these group elements, but then we're also going to, again, loop over the group elements and transform the grid defined over the group itself by these group elements. And in this case, the group action of a group element on a grid defined over the group is just a translation over the group, right? So essentially, if you have a grid which starts at the identity rotation, runs to rotation of 270 degrees, if you apply a 90-degree rotation to this grid, then this first element will move to the element corresponding to 90 degrees. And the 270, the element that corresponds to the rotation of 270 degrees will move to the 360 degrees rotation, right? So it just shifts essentially along the group axis. That's this shifting motion in green here. And then we normalize the group elements again because this interpolation function that we use requires this from us. And so this looks extremely complicated and it's very weird, but this just combines the transformed spatial grid and a transformed group, a grid over the group, into a single grid defined over the entire group. You don't have to implement this yourself. I'll just give this to you. Oh, yes. This counts the number of elements in a tensor. So this is a tensor, and this just counts essentially how many group elements there are. Okay, so we've now defined our kernel grid and the transformed version of our kernel grid. And just to inspect the shape that we have here. So this kernel grid has this specific shape, which corresponds to, so it's, each of its elements are three-dimensional because we have two spatial axes and the group axis, right? So that's three. We have we applied 4 rotations to this original grid, right? We have 4 separate rotations for which we have applied the group action. And then the kernel itself is defined over the group, so over something with dimensionality 4, which is the number of group elements again, and then kernel size by kernel size. Does this shape make sense to everyone? And then we can again visualize these kernel grids. So now each of these 4 visualizations corresponds to the application of the rotation action to this grid defined over the group. So as we can see, maybe it's a bit hard to see on the screen. Maybe just, can I zoom in a bit? I can. Sure. So if we follow this blue X, which is in the lower corner here, we can see that it does this twist shift motion that we saw previously, right? So this point moves from the first spatial feature map or first spatial grid to the second, and then to the third, and then to the fourth, while also rotating over spatial domain. Okay, so we've successfully implemented the group action on our grid defined over the group. Then now we're just going to define our kernel function again, which we'll use to sample the transformed kernels. So now we define the weights for our kernel function again. And the difference between this weight and the weight that we had in the lifting convolution is that now we have this additional rotation dimension in our feature map, right? So this additional dimension also shows up in our kernel function. So the only difference with the lifting kernel that we had previously is that our kernel is now additionally defined over the rotation group. So it's able to vary freely over the rotation group as well. Does that make sense to everyone? I hope so, and otherwise, I think if you go through this yourself, then you'll get a better understanding for it as well. Okay, so we initialize these weights again, and then we implement the sampling function. And now we apply the same trick that we did previously. We fold the input and output channels into the same dimension. But now, since our grid is defined over this 3D space, like 2 spatial dimensions, 1 orientation dimension, we're going to use trilinear interpolation instead of bilinear interpolation to reflect this additional dimension that we have, right? So we just simply loop over all group elements again and apply the, or interpolate the original weight using the transformed grid. And we stack these weights to end up with our full filter bank. And here we just simply separate the input and output channel dimensions again, and we apply the same reshuffling of dimensions to end up with a weight with the following shape. We're gonna inspect now. So the transformed set of kernels over the group has this shape, with this 8 corresponding to the number of output channels. This is the number of, let's say, output group elements. So this is the number, corresponds to the number of rotation transformations that we applied to our kernel grid. This is the number of input channels, and this is then the domain over which the kernel itself is defined. So 4 group elements, and then 5 spatial elements in either direction.
Okay, can I add some intuition here?
Of
For me,
course.
what's helpful understanding this, if you code this up, you have all these access and these reshaping and transposes, and what's happening in these convolutions is all these inner products, right? And with the inner products, you multiply, and then you sum over the spatial locations, the orientation axis, and the input channels. So that's all the things in the input that you match over. So that's the spatial axis, the orientation axis, and the input channel. So those are the things that are taken into account in this inner product. And then you repeat this for all output channels. So suppose you don't have this rotation axis, then you say, I'm going to generate output channel 1 with this particular kernel, which generates via this input, well, this particular channel. Then I step to the next output channel, output kernel, that's a kernel that generates the next output channel, and then the next, and then you repeat that for all rotations. So that's why you can also merge these two axes because you can think of it as just repeating the same kernel for different rotations, and also so thereby creating different output channels. And I hope that helps. Just a comment on it.
Yeah. Okay. Now we'll quickly visualize the kernels that we created. So because this is a sort of a thing defined over a 3D space, we flattened the group dimension into the first spatial dimension. So essentially we have stacked the different spatial kernels that correspond to different group elements along the first spatial dimension. So what you see happening is, again, this twist shift motion. Just follow this red square, I guess. You can see this twist shift motion happening to the kernel function itself, right? So these are the different group elements, so the different rotation transformations that we apply to our kernel function. And we can see that the kernel indeed rotates and shifts along the group axis, right? And we have 2 separate channels. Yeah. Does that make sense?
Sorry, what are the colors? Did you just go through that in more detail? Like what we're actually looking at in this graph?
Okay, so the colors correspond to basically magnitude of weights. So a more yellow color is a higher value for the weight.
It doesn't really matter for this figure, right?
No, yeah, but
It doesn't really matter for this figure. Yeah.
but just to clarify, yes.
What are those stacks actually representing? So the kernel is it rotates the red one. What are those stacks then?
So these are actually the 4. Yeah, these are actually the 4 group elements over which our input function is defined. So let's go back to this figure here. I've basically just sort of taken these 4 layers, these 4 spatial layers, and sort of concatenated them all together in one go.
These 4 layers represent again
The cyclic group, 4 rotations, right?
Yes. So these are the 4 sort of group elements over which your input feature maps are also defined.
Why does every of those layers only have one blue dot on that representation, that three-dimensional one?
This one?
Yeah.
So the blue thing is just, I added that so you can actually see what the transformation happening. If I didn't add this, it would just be all red and then you can see. But it doesn't mean anything special. It's just that we're basically tracking this single group element along the group.
So in those columns, then you cannot identify, because I'm trying to see any kind of rotation where how they're built.
Okay, yeah. So you could identify it. So let's say that this blue square corresponds to the top left pixel here. Then in this
Yellow patch is easier to track.
okay, let's say that it corresponds to this blue thing. Then this blue thing under the group action moves up essentially one group element and over because it also rotates. And so that's the same thing that we see happening here. So it moves up or down because the thing is the other way around, but it also rotates. So this yellow patch moves there.
I mean, like within the column itself, you're not able to see any kind of rotations or any kind of
No.
construction.
Yeah. So that's actually a good point. So that is because our kernel function is defined over the entire group. So it can vary freely. So these are just, all of these pixels correspond to different roto translations, right? In our input. So we have a feature map which is defined over the group. Goes from G to R. So for every group element corresponds to a location in this sort of stack of spatial things. And our kernel, similarly, is just a function which maps from this set of roto translations to real values. So it's a function defined from all the points in this sort of stack of group elements to real values. And it's able to vary freely over this set. Does that make sense?
So would you expect that like once you train, those end up like being really sparse because the input data is only over the original two-dimensional grid, but now you've kind of like split it out over more dimensions. And so each orientation, each point can kind of only coincide with one orientation, if that makes sense.
Yeah, that's an interesting question. I don't think that it would necessarily become sparse because, so you do go from this like 2D function to a function defined over group by this lifting operation, which sort of separates orientational information, right? So it extracts features under different orientations. As we just saw, these group convolutions actually then sort of extract features based on sets of relatively oriented features, if that makes sense. So let's say that we have these this face detector. We want to be able to detect happy faces. Then we would want a filter somewhere that's able to extract eyes which are upright and a mouth which points downward, for example, right? Yeah. So these would correspond to activations at different locations in your feature map, right? Different locations along the orientation axis, I should say, right? So your mouth points downwards, for example, but your eyes point upwards. And this specific combination of features is a happy face, let's say. Then if you train a network to extract this or to learn this function, then you'd like it to be able to sort of extract these sets of relatively oriented features, which would imply that your kernel function isn't necessarily sparse, right? Does that make sense?
Well, because I was thinking like each eye, like an eye has an orientation, but there can only kind of only be one orientation at each XY point, if that makes sense. Or am I thinking about the wrong way? Like there can't be two eyes occupying the same point in XY space that have two different orientations because like that point in XY space is already taken up.
But the kernels have to account for different orientations.
So it's not that sparse, and ideally, this is maybe if you have this stylized image representation, it's the case because you never encounter
Yeah.
an eye and like this in the same time. But suppose you have a feature like a crossing. This, if you pull this apart in this position orientation space, so I have this group volume with an x, a y, and a theta axis, and then maybe one line is picked up, you know, in this slide, so theta 0, that's the horizontal line, and the other line is picked up in the other slice. Yeah. So in the lower level feature, you only would have needed one single lifting convolution kernel, let's say, that was a line detector, and it would have generated this thing. And with this, now you can make a distinction between just a straight line without any crossings, because if you now detect a pattern here, I see only one peak, but if I want to have a crossing detector, for example, then the neural network, the 3D kernel could detect a kernel that tries to pick up a peak somewhere over here, another peak at a different layer. So you can have multiple features at the same spatial location, but which have different orientation.
Actually, I should start training the thing, otherwise it's gonna take forever.
Just
Okay.
start to run TensorFlow.
Yeah, I'll actually start running the model because I realized it's gonna take a little bit. Okay, I think we're almost there. So is this, I guess this is quite an important thing to sort of grasp what's happening here, why these kernels vary also over the group dimension, and to understand the action that you see happening here, this twist shift action. So is that clear for people? I could try spend some more time on it, but maybe it's a good idea to move on, and then if you start playing with it yourself, you'll probably figure it out. Actually, I see that I'll quickly do the rest of the notebook, and then you'll also have some time left to play around with it yourself. I've been going a bit slow, I see. So the last thing to implement now that we have our kernels is the group convolution operation. And this is very similar to the lifting operation, only with one difference, is that our input feature maps now also have this rotation axis, right? So with the lifting convolution, we sort of reshaped our input, the output channels and the group dimension, we reshaped it into the same dimension, but now our input feature map also has a group dimension, right? So it's defined over the spatial domain, but also over the group. There's the group axis. And because our convolutional kernels extend over the entire group, we can sort of apply the same trick that we used previously to fold the group axis into the output channel dimension. We can use the same trick on the input feature map to fold the input group dimension into the input channel dimension. Because our convolutional kernels extend over the full, you're basically doing as Eric was saying previously, you're basically doing an integral over the entire group, right? So normally with normal convolution operations, you sort of do an integral over an area which is kernel size by number of input channels, right? That's what you do normally, essentially. But now we do an integral over something the size kernel size by input channels by group dimension. But as you can see, the input channels and the group dimension in the input are basically treated the same. You're just summing over them. So you can fold them, again, you can fold them in the same direction or in the same dimension. And we apply the same trick with the group elements in the output. Does that make sense? This is definitely the most difficult part, I would say, of this whole notebook to understand.
Yeah, so again here, like you should remember that the convolution operator just does summing over all the input channels, and so since we also have to sum over the orientation axis, we might as well just flatten it together in the input channels plus the group axis together.
Yeah, but yeah, I left some hints I think up here. So I would recommend going through that, and then I think you'll get it. It's not that complicated. Just took me a while to understand what's happening. And then we can still just use the normal conv2d function in this case, because we apply this trick. So after we've done this, we reshape our feature map back to a feature map defined over the entire group again. And that's it essentially. And now we can start using these modules to create an equivariant CNN. So that's what we do here. We have a group equivariant CNN, which consists of this lifting convolution, which is the lifting convolution we implemented previously. And then we just add a bunch of group convolution layers. And at the very end, so again, we want these equivariant feature extraction operations because we want to be able to detect relatively oriented information. Essentially, you want to be able to extract these features which consist of multiple features under relative orientations to each other. But in the very end, we would like to be invariant because we want to do invariant object classification, for example. So then we simply apply a projection over all the remaining spatial and group dimensions. So it's basically a pooling operation over 3 dimensions into a single point. And then finally, we have a linear layer which classifies the extracted features. And then our network forward pass is simply applying the lifting convolution, some normalization, activation function, and then the same for the group convolutions. And then in the very end, we project feature map from the feature map which is defined over the group to a single point, and then we classify the resulting feature essentially. And we also implement to compare a normal CNN, which just consists of a bunch of conv2d operations with a similar architecture. And we'd like to, yes, question.
Why do you use an average over 3 dimensions, but in the group equivariant CNN? Use an adaptive average tool?
Yeah. Yes.
Why not max pooling?
You can also do max pooling. It's just a matter of engineering, I would say. I intuitively always like average pooling more because I guess you sort of, if you do max pooling, you're extracting only a single point essentially from your feature map, right? For every feature. And with average pooling, you're sort of at least averaging over all the features, different features that you've extracted. So this is just a design choice, but you could also use max pooling, yeah. Okay, to test our implementation, what we're going to do is train on the normal MNIST training data set and then evaluate on a test set, which is randomly rotated between 0 and 2 pi. So we're essentially training on a data set which has a very clear canonical orientation, right? All the images in MNIST are upright. And then we're testing on these randomly rotated versions of these images. And what we would like to see happening is because our network is invariant to rotations, we shouldn't see too big of a degradation in performance. But the conventional CNN should not be able to transfer performance too well to this test set because it's only ever seen these upright images, right? And it doesn't understand that if you rotate a 6, it could still be the same object. So to the normal CNN, these are 2 completely different things. But to our superior group equivariant CNN, they should be quite similar. So here are some examples extracted from the train set with the augmented test transformation. So as you can see, we randomly rotated a bunch of them. This is just a data loading module. And here we define a training function for our model. You see the normal CNN, which trained first, is already done. It gets a validation accuracy of 46%, which is still actually quite impressive, I would say. So training on canonically oriented MNIST digits and then validating on randomly oriented digits yields a performance in this case of 46%. So about a little bit less than half of the images are still apparently recognizable to the CNN, which is interesting. I mean, it could be that just if you rotate, for example, a 1 by 180 degrees, it still looks like a 1, right? So there's probably a bunch of this sort of stuff happening. And we're also training our GCNN now. It's been going for 80, it's almost done. As you can see, the performance is actually a lot better. So this model has only been trained on MNIST data, which has this very specific upright orientation. Testing it on randomly rotated versions of this data set still yields a performance of 90%. So why isn't it getting 100%? Does anyone know? So we're randomly rotating each of the images with a rotation, a continuously sampled rotation between 0 and 2 pi. So why would our model not be able to classify everything correctly? There's a bunch of hands going up. Go ahead. That's one of the reasons why. Yes, yeah. So if you rotate a 6 by 180 degrees, then you just end up with a 9. So it's always going to be hard. In practice, people have investigated this, and sometimes the network is still able to classify correctly, because apparently there's a difference between the way you write a 6 and a 9, which makes sense, I guess. But there's also a different reason as to why we don't get.
For example, the 90 degrees steps.
Exactly.
The rotations might be anything.
Yeah. So we've still made this discretization of our rotation group, right, into 90-degree rotations, whereas the dataset we're actually sampling consists of continuously sampled rotations between 0 and 2 pi. So our network is only fully equivariant to 90-degree rotations still, and it only approximates equivariance for anything in between. So that's, I would say, the biggest reason probably that we don't get better accuracy than this. So these are the final results. So you can see that with a similar number of parameters, our GCNN is able to outperform the normal CNN. An important thing to mention is that because our weight matrix for the group convolutions now has an additional dimension, we sort of require more parameters for a single convolutional layer, right? So in this experiment, the original, like the normal CNN, has a larger number of hidden channels than the GCNN. So there's this trade-off between, I would say, equivariance and model capacity. But in this case, it's still beneficial, clearly beneficial to use our equivariant model. So now we're gonna finally have a look at the activations throughout our model. So we take this input image. I think we rotate it a bunch of times. And first we apply it to, or we apply the normal CNN that we have trained to this set of rotated images. And what I've visualized here is the activations in the last convolutional layer for one of the channels. So as you can see, if we the different columns correspond to differently rotated input images. So we can see there's very little consistency between these feature maps, right? So if our network was fully equivariant or fully invariant, then we would like to see these activations also rotate with the image. But instead here, the activations just really change. So then we visualize the same but for the group convolution, group convolutional neural networks. And now we should be able to see, let me see how to interpret this again. We should be able to see the different activations translate throughout the network. Yeah, so our GCNN is equivariant to 90-degree rotations. So going from 0 to 90 degrees, we can see this twist shift motion that we saw previously happening. So this feature moves over there, right? With this twist shift motion again, and moves over there, etc. So for 45-degree rotations, you see there's still quite a difference in activations, which makes sense, right? Because we don't have a network which is equivariant to anything in between 0 and 90-degree rotations. Okay. And then finally, just as a final sort of inspection of our model activations, we're visualizing here the features extracted at the last layer after pooling. So after the last convolution operation, you do apply a pooling operation, you end up with a single feature vector with a number of channels, right? And we visualize this for the differently rotated images. And so this is for the normal CNN. As you can see, there's really very little consistency. So essentially, these are the features that our network has extracted, and these are the features that the linear layer uses to classify the input image. You can see these change quite dramatically as we rotate the input image for the normal CNN, because we're not invariant. But if we do the same for our GCNN, then we see that for every rotation, even for rotations in between 0 and 90 degrees, it obtains the same activations. So these essentially show that if we rotate our input image, the network is still able to extract the exact same set of features, which means that our classifier, the final linear layer, will classify these different images the same. Yes?
Why is it not just invariant to the multiplus of 90 degrees?
Yeah, that's a good question. Yeah, so I guess the network, so we're just discussing that you could also obtain invariance of your network by just having enough rotation augmentations. Maybe the images in the training data set aren't all canonically oriented. They maybe rotate a little bit. So maybe the network just learns to average these smaller rotations out. That's what I think might be happening, but honestly, I don't really know.
Yeah, it looks suspiciously similar.
Is it exactly the same? It's not
No,
exactly
it's
the same.
not exactly. No, look at this.
Okay.
Look at the
These are
final.
the two.
Oh yeah,
Look
They're
at
not
the
exactly the
They're
same.
not exactly the same.
And it's every four, it's always at 190 degrees where they have that.
Yeah, but it does make sense that these, like 45 degree and 135, are the same, right? Because these are also multiples. Yeah.
Right, every 90 degrees.
Yes.
But then you always have the 0 and the 90, they're almost exactly the same. And 45 and 125, they're okay.
Yeah.
Yeah, maybe it also has to do with smoothness of these kernels and you have correlation between feature maps also spatially, right? The activation of
Also.
and so also here maybe you have some smoothness along the orientation axis, and if you were to sample something in between here, then it would fall.
You don't believe it? You don't believe it?
Oh, I do.
Yeah. So I think, yeah, that's the whole of the notebook. So any final questions? I've gone a bit over time. I wanted to spend an hour on this, and then you'd have some time left to program it yourselves. We still have about 10 minutes, I think, left now.
I want to mention that so this builds GCNet from scratch. I just uploaded to Canvas to our modules mini Canvas page some links to other libraries that coded this up already, including actually David's a paper on separable group convolutions. Like this is based on interpolation of the kernel, but you could also parameterize the convolution kernel with MLPs and then dispatch from the grid and then sample the kernel. So I also put a link to your GitHub repo for this. Yeah, so check it out. Interested in this.
Any final questions? Yes.
Well, here we talk about rotations, which are cyclic, so you can have this nice property that can somewhat cover the possibilities.
Yeah.
If you look at something like translations, which has an infinite possibilities, how would you modify this to accommodate that?
Yeah, so for translation specifically, so in the end, using regular group convolutions, you will always need to make a discretization of the group that you're working with. So for translation specifically, you always sort of do this with CNNs, right? Your input's always defined over a discrete set of points, and you could apply or implement a convolution operation which sort of works on a higher resolution grid. Like you could subsample convolutions, but I don't see the point of doing this. I don't know what kind of features you would be extracting. But the point that you make is a good one. Like if you apply, the rotation group is very nice in the sense that it's cyclic and it's easy to implement group convolutions for that. But if you work with the dilation groups, a group of scaling transformations, you run into all kinds of weird problems. One of them being you need to, so the rotation group is cyclic, so you keep rotating, you end up at the same point, but for scaling you can go on infinitely in principle, right? You can scale something by whatever you like. So you have to sort of truncate your group at some point. You just, I guess, pick as a hyperparameter the factor to which you would like, scaling factor to which you would like to be equivariant. But then because your group is not cyclical, you also run into boundary problems. And there's, with scaling, you also have aliasing issues. So if you apply a scaling operation to your kernel, if you scale it up, for example, you don't want any frequencies contained in this larger scale kernel that weren't contained in your original kernel, because well, you're not going to be equivariant to a scaling transformation to the input if you do this. There's a bunch of nasty little details that go into other types of
for
groups.
scaling groups, they like these details have been worked out by David, but also other authors that do scale equivariance. So with the non-compactness of the group, I don't consider that much of a problem, because also with translational convolution on a large scale, also have an image, and you can decide to do zero padding to keep the image size the same, right? Also, that's like a function on the translation group, is to translate the kernel infinitely. So there you make the decision, okay, I'm just truncated and pad it with zeros. And that's also, if you do scaling, you add a scale axis, you can also say, okay, I'm going to move my kernel around and assume that the signal then continues with zeros to just cut it off at some point. So it's the same kind of tricks for group inputs that you already do for conv2D.
Any final questions or remarks? Or else you can maybe spend 5 minutes implementing group convolutions yourself. Yeah, this is the end of my presentation. If there's anything you're still struggling with, you can also just we can also just have a discussion about it now, one-on-one maybe. I can stick around for a while after the work college as well.
Right? Thank you, David.